Welcome everybody. We are happy today to have as a speaker Professor Youssef Boudabbous from the University of La Réunion, France. The topic of research of Youssef Boudabbous are around graph theory, reconstruction of diagrams, decomposition of diagrams, and structural study of prime graphs. And in these topics, Professor Boudabbous has around 50 papers about this subject. So today, I mentioned that Professor Youssef Boudabbous was a professor in our university some years ago, and now he is at the University of La Réunion. So the talk of Boudabbous today is applied on the minimal graphs, on the minimal prime graphs. So we can start, Professor, please.
Okay, thank you, Rafiq. Thank you for all the organizer of Applied Math webinar and all the participants. Shukran lil jamia, and I will start. Okay. The subject is the minimal prime graphs. I will present the evolution of this problem and the evolution of ideas and tools. Okay? It isn't a sample paper. Okay? We start as the abstract. Consider a graph G. A graph here is an ordered graph. Thus, it is an ordered pair of a set of vertices and a set of edges, which is a set of unordered pairs called edges. A model in a graph is a vertex subset such that every vertex outside is adjacent to all or to none. Thus, it is undistinguishable by any vertex outside. This notion model, there are many terminology. It is also called the interval of the graph, or clan of the graph, or homogeneous set. And for I say call this notion interval because this generalizes the notion of interval of R. Because an interval in R with its total order is a set of elements such that any vertex outside either is less than all the elements of this interval or is greater than all the elements of this interval. Thus, it is a set of real numbers which are undistinguishable by any real number outside. Thus, this notion generalizes the notion of interval in R. As example of model in any graph, clearly the empty set, the singleton of vertices, and the vertex set are trivial models, called the trivial models. If a graph has only the trivial models, it is called undecomposable graph. For example, any graph with at most 2 vertices, all graphs are finite here, okay? A graph with at most 2 vertices, it's trivially undecomposable graph because any vertex subset is empty or singleton or the vertex set. On the other hand, any graph with 3 vertices, it is easy to see it has a 2-element vertex subset, which is a model that is a non-trivial model, and has any 3-vertex graph is decomposable. And undecomposable is decomposable. Okay? Undecomposable graph with at least 4 vertices are called prime graph, as the prime numbers. Okay, we start by 2, not by 1. Okay? The notion, the central notion of this talk is the minimal prime graph. It is a graph. A graph is called minimal for a vertex subset if it is prime, but there is no proper subgraph containing this subset, which is prime.
He wants us to.
It is prime and minimal for this property. There is no vertex subset proper vertex subset containing the vertex subset A, such that the induced subgraph is prime. Okay? And the K minimal, we say that the graph is K minimal if it is minimal for some set of K vertices. The first part of this talk concerns this notion. This notion was introduced by Hill and Cornet. Okay? The first part of this talk concerns the first result of this notion, that is the description of the one minimal graphs and the two minimal graphs. Then we present the description of the three minimal triangle-free prime graphs obtained by Al-Zuhairi and myself. In the second part, we present a recent description of the three minimal prime graph in general. With Al-Zuhairi, we have characterized the three minimal graph without triangle. Okay? And with Fatma Rassini in his thesis, with Fatma and Muhammad Al-Zuhairi, Youssef Bouaziz, we obtained the description of all the three minimal prime graphs. Finally, in the last part, we give a recursive procedure to construct the minimal prime graph in general. Okay, thus we give a procedure to obtain the K minimal prime graph from the K minus 1 minimal prime graphs. This part is extracted from a recent paper obtained by Al-Zuhairi, Youssef Bouaziz, and myself, which is in the general case of diagram. Notice that even the result of Hill and Cornet concern the diagram. Okay, in the first section, preliminaries, we give some basic definition. A graph is a vertex, is a pair of vertex set and edge set. A pair AB of vertices is an edge. If a pair is an edge, we say that U and V are adjacent. Okay? U is a neighbor of V, V is a neighbor of U. Given a vertex, the set of neighbors is called the neighborhood and is notated NU. The complement of a graph is the graph on the same vertex set obtained by reversing all edges. A pair is an edge in G bar if and only if it is not an edge in G. And the induced subgraph is on a vertex subset X, is the graph on X such that the edges are all the edges of G formed by two vertices in X. The subgraph induced by deleting a vertex subset X, that's G induced by V minus X, is simply denoted by G minus X. A clique of a graph is a vertex set such that any two vertices in X are adjacent, and a stable set is a vertex subset in such that any two vertices in this vertex subset are non-adjacent. That is, the induced subgraph is complete graph. Any two are adjacent. Okay, and the stable set, it is a subset, vertex subset, so that the induced subgraph is an empty graph. Given a vertex subset X, we consider, for the notion of models, we consider vertices outside X. We say that this vertex is mixed on X if it is adjacent to at least one and non-adjacent to at least one. Okay? Thus, we say that it is not equivalent to X. Equivalent to X means that is adjacent to all the vertices in X or none of these vertices. The notion of isomorphism is natural. Okay, it is a projection of given two graphs a bijection between Vg and Vg prime such that uv is an edge of G if and only if FUFG is an edge of G prime. Okay, see the united isomorphism G isomorphic to G prime if there is at least one isomorphism. Thus, the notion of model or clone or interval or autonomous set of a graph is every vertex. A vertex is a model if every vertex outside does not distinguish the vertices in M. It is adjacent to all or none of X of M. The empty set, the singleton sets, subsets of vertices, and the full set are trivial models. And as I mentioned in the abstract, a graph is undecomposable if all its models are trivial. Otherwise, it is decomposable. And undecomposable graphs with at least 4 vertices are called prime graphs. It is easy to verify that given 2 disjoint models of a graph G, the behavior between any element vertex in X model M and N, the behavior of any vertex in M and vertex in N is constant. Either there is an edge between any vertex in M and any vertex in N, or there is no edge between them. Thus, we define the modular partition of a graph. It is a partition of the vertex set for which all the elements are models. If we have a modular partition, we can consider the quotient graph, okay, the G by P, okay, because the behavior is constant. Thus, we can define the vertices of the quotient are the element of this partition, modular partition, and 2 blocks or 2 vertices for the quotient, there are block of the partition, are adjacent in the quotient if and only if for any vertex in X and any vertex in Y, X and Y are adjacent in the graph. Okay? Another notion of models, there is the strong model. A strong model of a graph is a model which is comparable by inclusion with any model that it meets. Thus, if a model M is strong, if for any model N of G, if the intersection between M and N is non-empty, then either M is included in N or N is included in N. This notion is important for the decomposition theorem of Galai. We denote PG, given a graph with at least 2 vertices. We denote PG the set of maximal strong model proper strong model. That is the set of maximal strong model under the inclusion among the strong model distant from VG. Thus, we can state the result of the decomposition of Galois in the case of graph, okay? Because it is general now, we can state in the case of a digraph in general. Let G be a graph with at least 2 vertices. The set PG, the set of maximal proper strong model, is the modular partition, and the quotient of G by this partition is either prime graph or a complete graph or an empty graph. And this result proves the importance of the prime graph. Thus, there is a canonical partition of any graph by which the quotient is trivial, complete, or empty, or prime. Thus, the important case is the case that the quotient is prime. For example, it is not difficult to prove that almost all graphs are prime. The prime graph are important in the study of all the graphs. We define the frame of a graph, given a graph with at least 2 vertices. The partition of Galai PG is called the canonical partition of G, or the canonical modular partition of G, and the quotient G by this partition is the frame of G. And the notion of frame is important in this talk. Thus, here we give the definition of minimal graph. A prime graph is minimal for a non-empty vertex subset A if it is if there is no prime proper induced subgraph containing A. And in this case, we say that G is A minimal. We say that it is minimal for A or G is A minimal. Given a positive integer K, a graph G is K minimal if it is minimal for some set of K vertices. This concept was introduced in 1998 by Cournet and Hill. And in this paper, they described the K minimal digraph for K equal 1 or 2. Digraph in general. Right? Here, our talk concern only the graph, okay? But the result is general. The K minimal, the one minimal digraphs and the two minimal. It is not a characterization, it is a description. Okay? Then, with Al-Zuhairi, we described the three minimal triangle free graph. The problem of three minimal was difficult, very difficult. Pierre, I have a student with Pierre Sayar in Tunisia. I suggest that we can try to study the three minimality of graphs, to describe the three minimal graph. But Pierre considered that it is not the subject of a thesis. Right? It is very difficult. But with Al-Zuhairi, it is difficult, but we obtained the description in the particular case for the graph without triangle, which is more general for the tree, for example, or the bipartite graph. Then Al-Zuhairi described the four minimal triangle free graph when the subset A is not a stable set. Okay? He also obtained, he has another paper, but is not yet submitted for the case of, for element stable set. Recently, in the thesis of Fatma Arsini, we have described Fatma Arsini, Al-Zuhairi, Bouaziz, Monsef, and myself. We have described the general case of the three minimal prime graph, which is a very difficult problem. Okay. Also, recently, we have Zuhairi, Bouaziz, and myself. We gave a recursive procedure to construct the minimal prime digraphs. For example, from the three minimal, we have a procedure to obtain the four minimal. That don't mean that it is not easy after, but we have a procedure. Okay. We start by this remark, which is easily proven. Given a proper vertex subset A of a prime graph, G. If we consider a vertex subset B, including A, so that the induced subgraph GB is prime, and B is with minimum cardinality. Such B exists because VG included A, and G induced by VG is G, is prime. If we consider B with minimum cardinality from all the vertex subset, so that the induced subgraph is prime, including A, and the induced subgraph is prime, it is easy to verify that GB is A minimal. This remark, which is easy, shows the importance of minimal graph. Given a prime graph, for any vertex subset A, there is an induced subgraph containing A which is minimal. Thus, if we characterize or describe the K minimal graph, we obtain unavoidable induced subgraph by fixing the vertex subset. For example, we give the three minimal prime graph. At the corollary, we have a family, okay? Family F. In any prime graph, if we fix any vertex subset with three elements, there is an induced subgraph containing A, such that the induced subgraph is a member of our family. The second remark, if G is minimal for a subset A, then it is B minimal for any subset B, vertex subset B, including A. And thus, with these two remarks motivate our study with Al-Zuhairi and Bouaziz for the recursive construction of minimal graph. That's as I mentioned the first part. That's we present the 1 and 2 minimal prime graph obtained by Hill and Cournier by giving an idea of the sketch of proof. Then the result of with Al-Zuhairi on the 3 minimal triangle graph by giving the IDs and the tools of proofs, and we will see the evolution of tools. And then for the paper with Fatma, Al-Zuhairi and Youssef, I cannot present on the paper. It is very technical, very difficult, but I will present only the major tools to see the evolution of tools. And I invite the organizer of this webinar to invite Dr. Fatma to present this paper. Okay. And finally, we present the final, the last paper with Youssef and Al-Zuhairi on the recursive procedure for the construction of minimal prime graphs. In this section, we give some basic properties of models as the intervals of the set of real numbers, the empty set given a graph G, the empty set, the vertex set, and the singletons are models of G. The intersection of two models is a model. The union of two models having a non-empty intersection is a model. In general, the union is not a model, but if the two models, if the intersection is non-empty, their union is a model. Right? Here the trace, if given a vertex subset W, if M is a model of G, the intersection between M and W is a model of the subgraph induced by W. Given two models, if M minus M is non-empty, then the other difference N minus M is a model. And if two models are disjoint, then they are equivalent. There is a constant behavior between them. Now we give some result on prime subgraph, some structural result on prime subgraph. It is not difficult to prove that if a graph G does not contain P4, a path with 4 vertices, okay, 1 adjacent to 2, 2 adjacent to 3, and 3 adjacent to 4. If a graph has no P4 as an induced subgraph, then either G or its complement is disconnected. On the other hand, any prime graph, given a prime graph G, either G is connected, not either. Given a prime graph G, G or G bar is necessarily connected. Thus, any prime graph has an induced P4. Thus, in a prime graph, there is a small prime with 4 elements, with 4 vertices. The question, can I have a prime graph? In a prime graph, is there other prime subgraph with order 5, 6, okay? The following theorem of Ehrenfest-Rosenberg permits the construction of larger prime induced subgraph. Consider a vertex subset of prime graph such that vertex subset X such that the induced subgraph induced by X is prime. If outside X there are at least 2 vertices, we can add 2 distant vertices and we obtain a prime graph. Thus, in a prime graph, given a proper prime graph, such that the difference, cardinality of the difference is at least 2, we can add 2 distant vertices, and we have Gx union these 2 vertices. The set of these 2 vertices is prime. Thus, if we start by P4 in a prime graph, if our graph has at least 6 vertices, we can add 2 vertices to P4, we obtain a prime subgraph with order 6, and after with order 8. Okay. And if we have a prime subgraph with order 5, we can construct for each odd cardinality. But for order 5, it is not necessary. P4 is okay. P4, any graph, any prime graph has P4 as induced, but there are graphs with no prime induced subgraph with order 5. But if there is a subgraph of order 5, thus by this theorem of Ehrenfest-Rosenberg, for each cardinality, even or odd, for each cardinality between 4 and the order of the graph, there is a prime induced subgraph. For the proof of this theorem, we state the proposition 2, okay, below, of Ehrenfest-Rosenberg. And to state this proposition, we need some notation, which is a basic tool. Here we start to present the tools. Given a graph G, not necessarily prime, and a vertex subset X such that the induced subgraph Gx is prime, we will define some subsets of Vg minus X. We denote extension X, the set of vertices outside X, such that if we add X to X, we obtain a prime graph. We extend the primality of this graph. It is not an extension X. Thus, Gx union of this vertex is the vertex is an extension. Then the composability of this graph is extended. The Cauchy X is the set of X such that X is adjacent to all or to none of X. That is, X is a model of the induced subgraph, the subgraph induced by X union singleton X. Clearly, in this case, the union is decomposable. Okay? There is X is a model of Gx union X. In the first case, if we add a vertex in extension, we obtain a prime subgraph. Now, for given a vertex u in X, we denote xu, the set of X, such that if we add X, we obtain a model, the model xu, a model with 2 vertices, X and U. Okay? Thus, this subgraph is decomposable. We see the model xu. Okay? And if we use the notion of frame, this graph has a frame, has a prime frame. It has a prime frame, and its canonical modular partition is this pair xu and the singleton, the other singletons. And the result of Ehrenfest-Rosenberg, which is the tool to prove this theorem of Ehrenfest-Rosenberg. The first assertion, given a prime subgraph in a graph, the graph is not necessarily prime, but Gx is prime. The family denoted Px of non-empty sets among extension X, Cauchy X, and xu, where u belongs to X, form a partition of Vg minus X. Thus, it is a partition theorem of Ehrenfest-Rosenberg. We have a partition of the vertices outside a vertex proper, a prime proper vertex subset. Proper prime vertex subset. And now, by this 3 assertion, we have to add 2 vertices to a prime subgroup. We start with X, which is prime. And the question, if we add 2 vertices, what about Gx union xy? We add X and Y. These 3 cases, in these cases, we give the result depending the position of these vertices in the partition. Assertion 2, if X belongs to XU, thus it forms a model with U, and Y outside X union XU, because clearly, if we add 2 vertices in XU, we obtain a model with 3 vertices. Thus, we are decomposable. Thus, we don't consider the case 2 elements are in the same XU. But given you X in XU, if Y is outside XU in XU, if XU is a model, that is, if Y is not mixed in XU, clearly the union G induced by X union XY is decomposable because we have the non-trivial model XU. And in this assertion, we say that the subgraph GX union XY is decomposable if and only if XU is a model of this subgraph. And the other case, if X is in crochet X and Y is outside X and union crochet X, thus X is adjacent to all or none of X. If we add Y outside X union crochet X, if X union Y, if X is adjacent to all X and Y or non-adjacent to all of X and Y, clearly we have a model non-trivial, that is X union Y. And by this assertion, we have the equivalence. Gx union XY is decomposable if and only if X union Y is the model. Finally, if 2 distant vertices are in the extension, thus the union is decomposable, the G induced by X union XY is decomposable if and only if the pair, the added pair XY is a model. That is an important tool for the study of prime subgraph. As a corollary of theorem 1, since any prime graph has a P4, we can add 2 by 2 by 2, and we obtain a proper prime subgraph with order n-1 or n-2 if the graph is of order n. Thus, every prime graph with at least 5 vertices has a prime proper induced subgraph that omits at most 2 vertices, 1 or 2. This result was improved by Schmerl and Rutter.
الخطوة اللي جاية نعمل التقويم عشان نقدر نوزع.
There is a problem, Raviq?
No problem, Youssef. Sorry. No problem.
It's okay. I stopped the microphone.
Okay. Schmerl and Rutter improved this corollary by proving that there is a prime subgraph obtained by deleting exactly 2. Okay? If the graph has at least 6 vertices. And this last result, theorem 2, was improved by Pierre Hill and myself in the case of graphs having at least 2 vertices non-critical vertices. A vertex is critical in a prime graph if the deletion of this vertex gives a decomposable graph. Thus, if our graph, if the graph has at least 2 non-critical vertices, with Pierre Hill, we have proven that we can delete, we can find 2 distant vertices, X and Y, such that G minus X is prime, and then G minus XY is prime. Okay. Now we start the description of K-minimal graph. This section concerns the result of Hill and Cornet. Here I have a figure, the path Pn, the usual path Pn. Donc that is Pn, okay, the path. And the graph Qn, okay, we have a path V1, Vn minus 2, and we add Vn minus 1, which is adjacent to Vn and adjacent to V2, V3, Vn, only is not adjacent to Vn minus 2, it's adjacent to all vertices V1, V2, Vn minus 3. This is the figure of Qn. And for example, this graph is Q5. Okay? This is P4. The result of Hill Il Cornet, I give here the two results, k equal 1 and 2, given two distant vertices of an n-vertex graph with n greater than or equal to 4. The graph G is minimal for singleton A, that is, the graph is one minimal, if and only if G is isomorphic to P4, or there is an isomorphism from G onto Q5 such that FA equal V1. In this figure, P4 is minimal for any vertex. It is minimal for U1, U2, U3, and U4 for any singleton, but U5 is minimal for this vertex Q1. And we see that there is a P4 here, P4 containing V2, V3, V4, V5. It's not minimal for the other vertices, but it is minimal. There is no P4 containing V1. That is the characterization or the description of the one minimal graph. For the two minimal, it is the second assertion. The graph G is minimal for AB if and only if it satisfies one of the two assertions. There is an isomorphism from G or G bar onto Pn such that FAB equal U1 UN, thus Pn, and A and B are U1 and U1. This Pn is minimal for the pair U1 UN and its complement, okay, G or G bar. Either G is isomorphic to Qn with AB equal V1 Vn, the same position. But that's we give the isomorphism and the position of the vertices in A. Okay? Here we give a sketch of the proof of theorem form. There is no special tool on the prime subgraph. It is, I think that it is only a good use of the connected component of some subgraph. Okay? There is no difficult tool. And here we give the proof of the second assertion. Consider A and B to describe the minimum, to prove this assertion, the graph G, we call H our graph, and we will prove that there is a subgraph containing AB such that the induced subgraph is satisfies the assertion of the theorem. After that, we have to verify that this solution is minimal. Okay, but the idea is we consider any prime graph and two distant vertices. We prove that there is a vertex subset including AB such that G, the induced subgraph G equal H induced by X satisfies one of our two assertion of assertion 2. Okay. The idea is simple. We by interchanging H, notice that a graph is prime if and only if its complement is prime. A graph and its complement have the same models. Thus, a graph is minimal for a vertex subset A if and only if its complement is minimal for this vertex subset. Okay? Thus, we may, by interchanging H and bar, we may assume that A and B are non-adjacent. We consider the subgraph induced by deleting the intersection between the two neighbors of A and B, neighborhood of A and B. And we denote CA, the connected component of this subgraph containing A, and CB, the connected component of this subgraph containing B. We have two cases. Either CA equals CB, thus A and B are in the same component in K, thus there is a path. And this path, its length is at least 3, because there is no element in the intersection. The vertices in the intersection of the neighborhoods are deleted. Thus, if CA equals CB, by considering a shortest path between A and B, we obtain a vertex subset X, including AB, so that HX satisfies the first assertion. The second case, if CA different from CB, in this subgraph K, the components are models. In any disconnected graph, each component is trivially a model. Thus, CA and CB are models in K. Okay, but they are not models in G because G is H, because H is prime. Thus, if you consider the pair AB, if A and B, if CA equals singleton A and CB equals singleton B, thus the pair AB is a model in K, and any vertex outside is adjacent to all of them. Thus, the pair AB is a model of H, which contradicts the fact that H is prime. Thus, at least one of them is non-singleton. For example, CA, cardinality of CA at least 2. Now, we consider CA, since it is a proper subset, non-singleton, non-empty and non-singleton, that it is not a model because H is prime. Thus, there is a vertex in the intersection which is dilated, which is mixed on A and some other element in this compound, some other element that is A prime. By considering a path in K from A to E prime, and by considering the smallest I such that the vertex Z, which is mixed, is non-adjacent to UI, we obtain the graph Q. We obtain the subgraph satisfying the assertion. Thus, it is not very easy, but there is no difficulty. Okay. Now the result of Al-Khwarizmi and myself concerning the 3 minimal triangle free graphs. Here we give some figures. This graph is called SKMN. It is a tree. We have a path RA1AK, RB1BM, RC1CN. Okay, the same root, and we consider the union at the same root. Okay? This graph is PK, but we add the edge between 2 and 5. We denote PK to 5. We add this edge between 2 5, and this graph is P6, and we add the edge with 1 5. And the result with Al-Khwarizmi, given 3 distant vertices in a triangle free graph, the graph G is minimal for these 3 vertices if and only if one of this assertion is satisfied. P4, okay, small solution. PK says that XYZ contain the 2 leaves, the 2 ends of the path. SKMN and XYZ are the leaves, the 3 leaves. Okay. S12N, here there is another position, not 3 leaves. Okay. S122 is a small solution. Okay. P615 small solution, but it is here. P615, K25 it is here. For any K here, it is not small. And P625. Thus there is 8 families. Okay. Here for the proof we need the tools on the prime subgraph, the partition of Ehrenfest-Rosenberg as example. The proof use proposition 2. Okay, is not a problem of connectivity. Okay? The partition of Ehrenfest-Rosenberg and the effect of adding 2 vertices on the indecomposability. That's all the assertion of proposition 2 are needed in this proof. Okay. Here, this lemma is easy, but it is sample given if M is a non-trivial model in a decomposer, we give some lemmas. If M is a non-trivial model in a decomposer triangle-free connected graph, then M is a stable set. Moreover, if G is a tree, then all the elements of M are leaves of G. Leaves, that is vertices of degree 1, having only one neighbor. A tree with at least 4 vertices is prime if and only if any 2 leaves have not the same neighbor or the same father. Okay? And SKMN, this graph, is prime if and only if M greater than or equal to 2. Here K is less than or equal to M, M less than or equal to M. Okay? For the proof of the lemma 2, we consider 3 distant vertices of triangle pregraph. Here is the case if the induced subgraph is P3, we prove that there is a subset X including XYZ such that Gx is P4. Thus P4, the solution is P4 here. And if XY is an edge, there is a P4 including XY. Thus, lemma 3 is not difficult after lemma 2. Let A be 3 vertex subset in a triangle free graph. If GA is not stable, okay, that is P3 or P3 bar, the complement of P3. If G is minimal for A, then G satisfies the first or the second assertion of theorem 5. Then we consider the case of stable set. If A is a stable set, we have to consider two cases. If there is a vertex subset X such that Gx is P4, intersecting A in two elements, such that the cardinality of intersection X and A equal 2, then G satisfies one of all the conditions of theorem 5 except the first one. And the other case, we prove that G satisfies the second or the third condition of theorem 5. This section concerns the description of three minimal graph in general case. Thus here we use the partition of Ehrenfest-Rosenberg, and this result was obtained because the model is sampled. Any model is a stable set. Thus, if the model is large, inside the model we know that there is no edge, but this property helped the study. For the work with Fatma Arsini, Al-Zuhairi, Youssef Bouaziz, as I told, the presentation of this description need an independent presentation. I only give the major tools. I suggest that Dr. Fatma will be invited for such a tool. Here we give the tool. The first tool is the notion of chain introduced by Chinovisky and al. Given a graph, a sequence S0, S1, SP of distant vertices is a chain of G if for any I greater than or equal to 2, Si is the unique vertex in S0, SP, which is mixed in the preceding vertices, that is S0, SG, G small than I, small than I. Thus, V0, V1 are arbitrary, the behavior. V2 is, for example, adjacent to V1, but non-adjacent to V0. V3, adjacent or non-adjacent to V2, and it has the same behavior with V0, V1. Okay? That the structure is easy. From V2, we have two choices. Okay, V5, we have two cases. Either V5 adjacent to V4 and non-adjacent to V0, V1, V2, V3, or V5 is non-adjacent to V4 and adjacent to all V0, V1, V2, and V3. Okay? And a chain is called, in a graph, is called the prime chain if the induced subgraph is the prime, otherwise it is called the decomposable chain. This notion is important in this study. Notice that in their paper, Chinovisky and al., they characterize the prime chains and describe the decomposable chain. They are up to isomorphism for decomposable chain for any n. For the description of three vertex, for our description, we consider a three vertex graph H, and we describe the A minimal graph such that GA is isomorphic to H. Recall that H is any graph with three vertices is either K3 or K3 bar, the complete graph, or P3 or P3 bar. Here, I only state the following easy part of our description. It concerns the case where the graph G is a chain from a two-element subset B of A to the other vertex in A minus B. This proposition, let A be a vertex subset of G. If GA is isomorphic to P3 bar, then G is a minimal if and only if G is a chain W0, W1, Wn with n at least 3, such that W0, W1 is an edge, Wn minus 1, Wn is an edge. And A is a W0, W1, the two first vertices and the last one. And if GA is isomorphic to P3 bar, then G bar is the solution. Another tool is the same, the partition of Helmholtz-Rosenberg and the effect of adding two vertices, that is proposition 2. Another tool is another partition obtained by myself and Pierre of the vertices, not outside the prime subgraph, but outside a subgraph having a prime frame. It is more general.
Professor Youssef,
This part, what?
you have 2 minutes to conclude, please.
كيفاش نبيل؟ كيفاش
2 minutes. 2 minutes.
كم؟
دقيقتين.
كو.
Yes.
اوكي.
Okay.
ما لاحظت شيء. اوكي. Finally, recursive construction of the minimal graph. We generalize the notion of chain. We introduce the notion of strong chain, and we obtain a separation principle basing on the partition of Pierre and Boudabbous. I don't. That is this result. That is the major tool. We obtain separation principle, that is proposition 4, and then we give the procedure by this theorem. Given a prime graph G and K element vertex subset A, if G is a minimal, then either there is a vertex X in A such that G or G minus X is A minus X minimal, or there are a vertex X in a proper subset X such that including A minus X such that Gx is A minus X minimal, and we enumerate the other vertices S1, Sm outside the union, and we obtain either this figure, that is the other vertices. We form a model only Sm, here the notion of strong chain, and we know the behavior of these vertices, okay? And the other assertion, a prime minimal for A minus X by adding a path and some edges between the end of the path and the element of X minus A. Here we explain that our result is optimal in some way, okay? I have to mention that many other structural results on prime graph are obtained in some members of the combinatorial team of the University of Sfax, namely Professor Imad Boudabbous, Dr. Mohammed Yahya Sayar, Dr. Nada Al-Amri, Dr. Mohammed Bakal Aish, and Walid Marwan. And thank you so much.
Thank you, Professor Youssef, for this nice talk. With questions, if there are some questions.
Okay.
Yes, maybe.
Of course, I'm not a specialist of this topic, but I'm really interested by these results. And my question as someone who is not a specialist, what is the motivation of all of these results? And is there some examples of applications in any subject?
Okay, the first motivation that almost all graphs are prime. That's any structural result on prime graph is important. But I have many work on the reconstruction problems. Given a graph by some local condition of isomorphism, we have to obtain the graph up to isomorphism. And in many problems of reconstruction, the difficulty now is the prime graph. We don't know, we don't have sufficient result on this on prime graph. The difficulty of many problems in graph theory is, in particular in the reconstruction problems, is in the prime graphs. For this, we have to study many study in the as structural result on prime graph is needed.
In other words, are there any applications in networks or biology or something else of this prime graph, of this result?
Application is not for me. Is not for me.
I can, for example, I know.
But I have to mention that, as example, Michel Habib is in computer science. Is interested to prime graph and decomposition of graph, and they have the algorithmic point of view for the study of prime graph. And there is many study of he give algorithm to find the models of a graph, and there are researchers in computer science. They are interested to the study of prime graphs.
Yes, I know, for example, that.
What?
I know, for example, that there is a lot of applications and social networks and partial differential equations and discretization by finite element method. For example, we obtain some sparse matrix, and the graph theory can be very useful to understand the structure of these matrices. And it's here some examples, but my question was more specific: how these results can help. Okay, how it can help in graph theory. It's what we cannot see if we are not specialists. Okay.
In graph theory, the decomposition of graph is very important for algorithmic aspect or for many problems.
Mm-hmm.
Seymour, for one of the four authors, is not specialist in decomposable graph, and no, he has many papers on prime graph because it was an important tool. The structure of prime graph is important in application, but Youssef Boudabbous don't know the application.
Okay. Okay, thank you.
I haven't the time for application.
Okay, thank you.
Welcome.
Are there any extension in random graphs? The notion prime random graphs exists or not?
I ما سمعتش رفيق. I don't.
The notion prime random graphs. This notion exists or not?
Prime
random graphs.
Prime random graphs.
Your graphs can be a random or not. In other words, at any time, the text can be connected to the existing graph at random.
Well, there is the random graph في the radu graph, no? تحكي عن radu in particular ولا؟
No, in general.
I don't know. Okay. But almost all graphs are prime.
Okay.
That is the number of prime graphs is equivalent to the number of graphs in infinity, if n is the infinity. Okay. The limit of the quotient is 1. The limit of the quotient is 1.
Okay.
Not only the graph, for tournament, for prime digraphs in general.
Okay. Are there other questions, please? Other questions? So if no questions, we stop this session, and we thanks again Professor Youssef Boudabbous for this nice talk. And see you after 2 weeks. Yes, we shall receive.
شكرا سيدي. السلام عليكم. Thank you for السلام عليكم.
Thank you, Youssef. Thank you. See you.
Welcome. السلام عليكم.
بالسلامة.
السلام عليكم.
شكرا.
السلام عليكم. سينا بيك سلام.
اهلا وسهلا.
اهلا بيك. شنو حالك؟
وين انت سينابيل هذا؟
من نابلي.
نبيل arrête l'enregistrement.
في نبلة.
Okay.